We've all felt pain, right? From a tiny paper cut to something much more serious. But what if I told you it's not just a feeling? It's a message, a really sophisticated signal on an incredible journey through your body. And in this explainer, we're going to follow that signal every single step of the way.
So let's just start with the biggest question of all. We all know what pain feels like, of course, but what is it really? What is actually happening inside our bodies to create this sensation that can sometimes dominate our entire existence?
Well, at its very core, pain is a message. It's your body's own internal alarm bell. It's a protective system designed to tell you, hey, something's wrong here, and help you pinpoint the damage to keep you safe. It's a warning system, and you might be surprised just how incredibly complex it is.
Okay, so our story begins right at the moment of injury. This is part 1. The signal is born. Where does that very first ouch actually come from?
This is basically our roadmap. The signal's entire journey can be broken down into 3 main stages. It all starts with transduction. That's the moment the signal is actually created. Then comes transmission. That's its trip up to the brain. And finally, modulation, which is where the brain interprets the signal and decides what to do. So let's start right at the beginning, with transduction.
So the second your tissue gets damaged, it kicks off this chemical chain reaction, what we call the inflammation cascade. You can think of it like a biochemical flare being fired off. The damaged cells release this soup of chemicals, which then triggers a second wave that spreads the alarm even further. This chemical soup is the birth of the pain signal.
All right, so the signal is born. Now, it's got to go somewhere. It needs to travel. Welcome to part 2, the information superhighway of your nervous system.
Now, this highway has different kinds of lanes, or nerve fibers, for different kinds of traffic. And for pain, we really care about 2 main types, A-delta fibers and C fibers. And trust me, they're responsible for very, very different kinds of pain.
So here's how to think about it. The A-delta fibers, they are the express lane. They're insulated for maximum speed, and they carry those sharp, immediate pain signals. You know, the ouch of a paper cut. The C fibers, on the other hand, are the scenic route. They're slower, and they carry that dull, throbbing, aching pain that comes later, like with a lingering bruise. So, whether it's traveling on the express lane or the scenic route, the signal zips up a nerve to the spinal cord, and here it hits a super important relay station. The message gets passed to a new neuron, it crosses over to the other side of the spinal cord, and then it begins its final climb up to the brain.
But here's the thing. This system, as brilliant as it is, it's not perfect. Sometimes the wiring can get a little faulty, and that leads to some really distorted signals. So welcome to part 3, when wires get crossed. One of the biggest ways things can go wrong is through something called sensitization. After being stimulated over and over, the whole system can become hypersensitive. It's kind of like the volume dial on your pain system gets turned way up and then gets stuck there, lowering the threshold for what your body even considers to be painful.
Now, this sensitization leads to 2 really key malfunctions. First, you have hyperalgesia. This is when a painful thing hurts way more than it should. The classic example is a bad sunburn, where even a warm shower feels agonizing. And then you have allodynia, which is even weirder. That's when a normally harmless touch, like your clothes brushing against your skin, suddenly becomes painful. And then there's this absolutely fascinating phenomenon called referred pain. Just think of it as a GPS error in your brain. You see, nerves from your internal organs often share the same pathways in the spinal cord as nerves from your skin. And because the brain is so used to getting signals from the skin, it can get confused. It might misinterpret a signal from, say, your heart as coming from your left arm. This is exactly why a classic heart attack symptom is pain shooting down the arm. So, the signal has finally arrived. This takes us to the last stop on our journey, part 4, the brain's control room. This is where the message is finally read, interpreted, and acted upon. But here's the cool part. The brain isn't just passively receiving the message. Nope, it's an active manager. It actually has a whole dedicated circuit, a descending pathway, to send signals back down the spinal cord to turn down the volume of those incoming pain signals. It's like it has its own built-in pain management system. So how does the brain do this? It makes its own painkillers. That's right, it releases its own natural opioids, chemicals like endorphins, that actually block pain signals right at the spinal cord. This is the very mechanism that allows a soldier in the heat of battle to get a serious injury and barely even feel it until the danger has passed.
Understanding this whole journey, from injury all the way to perception, lets us do something pretty remarkable. It allows us to intervene. Let's talk about Part 5, Hacking the Pain System.
So now we have an intervention map for the entire journey. We can actually target the pain pathway at all these different points. We can try to block it at the source, intercept it during its trip up the spinal cord, boost the brain's own control system, or even alter the final perception in the brain itself.
And this is precisely what modern painkillers are designed to do. You've got your non-narcotics, like ibuprofen. They work right at the beginning, stopping that initial inflammation. Then other drugs can help boost the brain's own dampening signals during transmission. And of course, narcotics, or opioids, they work directly on the brain's receptors to change the final perception of pain.
But when pain becomes chronic, the problem gets so much more complex. The experience isn't just a simple physical signal anymore. It becomes its own disease state, and it gets deeply tangled up with our emotions and our psychology. To treat it effectively, you really have to address all these things together.
So, we end here. Pain becomes as a vital protective messenger. But as we've seen, that system can break. The signal can become distorted, amplified, persistent, and it leaves us with this final, really crucial question. What do we do when the warning message itself becomes the disease?